If you'd like to deploy your trained model to the Arduino Nano 33BLE Sense, head to the deployment page of the Edge Impulse project you made for Arduino. Feel free to do the model testing and live classification. They would work very similarly to what we did in the phone deployment lecture. Note that Edge Impulse gives us the option to build a generic C++ library. This is great if you want to compile for any number of microcontrollers, as long as you have access to a C++ compiler. To keep things easier, we're going to use the Arduino library in this course. Select that and scroll down. Keep the Eon compiler enabled, but let's chat for a moment about what that does. By default, a trained TensorFlow Lite model is converted to a flat buffer, which is loaded at runtime. The operations stored in the model are read and executed by an interpreter. The interpreter, at least the one for microcontrollers, was written in C++. Edge Impulse developed the Eon compiler based on work by the TensorFlow Lite community. Eon compiles the TensorFlow Lite model into C++ source code, and as a result, it saves RAM and flash space on the target device. Unless you need to use the base TensorFlow Lite interpreter, I recommend leaving the Eon compiler enabled. Click the Analyze button, and Edge Impulse will give you some idea of how long it thinks inference will take and the RAM and flash requirements for the library. Note that these estimates were calculated for an ARM Cortex-M4F running at 80 MHz, so you'll have to think about how the speed and architecture of your particular processor might affect these numbers. The Arduino Nano 33BLE Sense runs at 64 MHz, so inference time will likely be a little longer. Also, note that the inference time reported here does not take the feature extraction time into account. You'll want to go back to your processing block to get that estimate. You can select the floating point option, but I recommend sticking to the quantized option when deploying to most embedded systems. You'll lose some accuracy, but you'll usually save on RAM and flash space. When you're ready, click the Build button, and Edge Impulse will wrap your trained model up into an Arduino library for us to use. Note that you should not unzip it, as we'll import the .zip file directly into Arduino. If this is not the first time you've installed a library for your Edge Impulse project, you'll likely want to delete the old one from your computer first. Head to wherever Arduino stores libraries on your computer, find the folder named ei-your project name, and delete it. Then start the Arduino IDE. In it, click Sketch, Include Library, Add .zip library. Navigate to your Downloads folder and select the Edge Impulse library you just downloaded. That will import the whole library, which includes a few samples for us. Select Tools, Board, Arduino Nano 33BLE. Go to File, Examples, and find the library with the name of your project. From there, select the Nano BLE 33 Sense accelerometer sketch. Make sure your Arduino board is plugged into your computer and go to Tools, Port. Select the serial port associated with your Arduino. Click Upload, and while that's running, let's briefly go through the code. If you are familiar with Arduino programming, this should be fairly straightforward. At the top, the sketch imports the Edge Impulse library, which includes our trained model. Then it imports the accelerometer library that comes with the 33BLE Sense. You should see a few constants to help with some math, and a flag that tells the library to print out the internal workings of the neural network. In setup, it starts the serial port and the accelerometer, which is part of the IMU. This EI-printf function is defined just below setup. It allows the library and this top-level sketch to print things to the serial monitor over UART. You can see that it relies on the same serial.write function that you might be familiar with in Arduino. In Loop, we perform the data collection and inference in distinct steps. The program tells you it's about to sample, and then it samples for 2 seconds, saving each of the accelerometer's axis measurements to a buffer. When it's done, it converts the buffer into a NumPy signal array. From there, it calls the run classifier function, which performs the feature extraction followed by inference on our trained model. When that's done, it prints the predictions to our serial monitor. If you are on Windows, you might run into this error in Arduino, which tells you that the path of some of the files in the library are too long. To fix this, head to the Edge Impulse docs and search for On Your Arduino. At the bottom, you should see an embed platform.local.txt that you can download. We want the one for embed, as that's what our Nano 33BLE Sense is running. Copy that file to your username, appdata, local, Arduino 15, packages, Arduino, hardware, embed 1.1.4. Then try uploading your sketch again. When you are done uploading, change the port back to the original port of the Nano board. This particular Arduino has a habit of switching serial ports when it's done uploading. Then open a serial monitor. The program will tell you when it's about to sample, when it's sampling, and the results of the classification every cycle. While it's sampling, try moving the Arduino left to right. The label with the highest probability should be left-right. Try again with the up and down motion, and you should see the up-down label report the highest probability. Repeat the process for a circular motion. It should detect either clockwise or counterclockwise motion. Finally, try just holding the Arduino board still, and the program should list idle as the predicted label. If you head to your Arduino libraries again, which is in Documents Arduino Libraries for Windows, you can find where the project library was installed. It should be named EI-name of your project. Go into the source folder and into Model Parameters. Open model_metadata.h in an editor program. This is a useful file that contains lots of information and settings for the project. Note that while our smartphone data collected at a rate of 62.5 Hz, the Arduino board defaults to collecting at 100 Hz. You can change this in Edge Impulse, but for now, let's stick with 100 Hz. It also means that we have 200 samples of each axis instead of the original 125. Scroll down and you can see the array containing your labels. Note that the order of these labels matters, so if you want to reference the left-right label, you'll need to use an index of 2. Back in Arduino, go to File, Examples, your Edge Impulse library, and select the accelerometer continuous demo. This sketch is similar to the regular accelerometer demo, but it uses the Mbed OS to run data collection and inference in 2 separate threads. We won't get into multi-threaded programming in this course, but I'll briefly go over what's happening in this sketch to give you an idea of how you can use multiple threads to perform inference in the background. Let's start the upload process and look at the code. Setup runs first, which sets up the first thread. That thread is called a task in other real-time operating systems like FreeRTOS. Here, the run inference background function is called, which contains its own while loop. This thread works just like the inference section in the previous sketch. It copies in whatever is in the raw accelerometer buffer to a NumPy signal array and uses that to make a classification prediction. You can see that at the bottom of the loop, the thread only performs these operations about once every 200 milliseconds. Here, a smoothing operation is introduced that averages several inference predictions over the course of a couple of seconds to get us a more confident answer. Because of this, you will need to perform the motion for a couple of seconds before you see a good result. The main program loop works much like its own thread, operating independently of the other thread. Here, it rolls the buffer forward 3 points, which drops off the oldest 3 raw data points. Then it reads from the accelerometer and stores the new samples at the end of the buffer. It waits the necessary amount of time so that it can continue sampling at 100 Hz. When the upload process is complete, open a serial monitor and take a look at the output. The DSP measure tells us how long it takes to perform feature extraction, and classification tells us how long it takes to perform inference with the model. We have not enabled the anomaly detection part yet, so ignore that for now. Then you should see which class has the highest confidence score, followed by an array of 6 numbers. These numbers represent the smoothed or averaged predictions and are given on a scale of 0 to 10, where 0 is the lowest and 10 corresponds to 100% probability. The first 4 labels line up with the classes. As I let the board rest, the second number should be 10, and the sketch tells me that it thinks the board is idle. If I move the board in a circle, the first element begins to rise. When it gets above 8, it will give me circle as the predicted class. However, during the transition, or if I move the board erratically, the 5th element will rise, which corresponds to the level of uncertainty. The third element is the left-right label, which you can see go up as I wave the board back and forth. The fourth element is up and down. After moving the board up and down for a while, the confidence score will be high enough to change the predicted label to up-down. The final number represents an anomaly score, which we won't get into yet. In the code, you can see that the smooth update function outputs the predicted label for us in addition to giving us these confidence scores. I recommend starting out with the simpler single-threaded example to get a feel for how data collection and inference works on a microcontroller. As you continue your embedded machine learning journey, you will see that concurrently collecting data while performing inference in the background will likely be necessary. At that point, I recommend coming back to this demo sketch or looking at other multi-threaded examples to see how they work. Note that you can rely on other techniques, such as simple timer interrupts or direct memory access, to collect data in the background as well.